Hi, I'm Eric Jacobsen. Today we're going to give a little explanation and a demonstration on what is aliasing in sampled systems. Basically, what is aliasing, why is it bad, and how to prevent it. We're going to give some demos too, basically showing aliasing happening in some examples actually that you've probably seen before and maybe never realized what was going on. And we'll have a graphic explanation too that diagrams a little bit better explanation of what's happening in the frequency domain. Now we're not going to go into a lot of math. It's mostly going to be an intuitive explanation because there's already videos on YouTube showing the math in pretty good detail and doing actually a pretty good job of showing the math. Plus you can get it from a lot of signal processing textbooks, so we don't need to do that over again. What's missing in a lot of cases, though, is a good intuitive demonstration and explanation that can go along with the math, and so that's what we're going to do today. A sampled system is a system that takes discrete samples in time, and a really good example of that is a movie. You know, the old 16 millimeter or 35 millimeter movies, or even the little home 8 millimeter movies that sampled what was going on in front of the camera by taking frames, by taking basically a snapshot in time at the frame rate, every frame. And you could look at the film and see the frames and see this is an instant of what happened at that frame time, and then the next frame was what happened after some delay at the next time. Now what was not recorded was what happened in between those frames. And so that's the difference between continuous time, which is the world we live in, and discrete sampled time, which is what we have in digital systems and in things like movies. So we're going to use a video sampling technique using a strobe light to show an aliasing happening in a sampled system using the strobe as the sampler. And it'll be very similar to what happens in a movie. If you're familiar with seeing the wagon wheels turn backwards, or wheels turn backwards, or at a funny rate, or propellers turn at an odd rate in a movie, that's aliasing in a sampled system. And so we're going to show you some of that with an explanation and tie it into the graphical explanation of what's happening in the frequency domain, and hopefully pull it all together for you and make it a little more understandable. Our test apparatus, our demonstration apparatus, our experimental apparatus, whatever you want to call it, is going to be this helicopter. And we're going to make the blades rotate, and we're going to sample it in time, with discrete time, with this LED strobe light, which we've had to modify a little bit. And one of the things that we've done to help make the demonstration go a little bit better is we've put a mark on one of the blades of the helicopter, and what we've done is put a reflector here and then put dark marks around it, only on one tip of the blade. Because what happens in a sampled system is as the blade's turning and you're taking snapshots of it, you only see the blade in certain positions because it's in discrete time now. Like in the movie, we're taking only frames of it in particular positions, and that's why you see it maybe turning backwards or something like that, or propeller or wagon wheels. So in the demonstration, we're going to watch what happens with the marked blade and the unmarked blade, because what happens, one of the things that we're going to be looking for is when something is rotating at exactly equal to the sample rate. In other words, we take a sample and we see the rotor, say, in this position. If it rotates exactly one full time and then we sample it again, it looks like it hasn't moved. And that's aliasing, because the alias is it's masquerading as not moving when actually it is moving. And that's for so when something happens at exactly the sample rate. In other words, when we get one full rotation for every sample, it's going to look like the blade's not moving. If it's moving slightly faster than the sample rate, it's going to look like it's moving very slowly, when in reality it could be moving quite fast. And how fast? Actually, in a sampled system, we don't know, and that's why aliasing is bad. If you take a snapshot and the rotor's right here, you take another snapshot and the rotor's right here, you don't know if the rotor actually did not move at all, or if it moved one full rotation, two full rotations, any integer number of rotations could have happened and gotten that exact same result. So this is why aliasing is bad in an instrumentation system, or when you're sampling for signal processing or something like that. And that's why it's called an alias, is because you can have input signals that masquerade as other input signals, and you cannot tell them apart.
So here we see the rotating blade, and one of the tips is marked with our reflector with the black around it, and the other is bare. And we can see that right now, as it's still, the rotation rate exactly matches the sample frequency from the strobe. And it's rotating either backwards very slowly or forwards very slowly as the rate changes a little bit from the sample rate. We can't quite synchronize the rotor with the sampler, but this is pretty close.
So we just demonstrated with the strobe light sampling at 12.5 hertz that we saw the rotor appeared to be moving very slowly. Now, because the video camera samples a lot faster than that, we could also see the blur of the rotor moving, and so we knew that it actually wasn't moving at the slow rate that the strobe made it seem like. But if the strobe was your sampler, it would have appeared that the rotor was moving very slowly, either forwards or backwards, and we knew it was actually moving about 2 revolutions between each strobe sample. So that's a really good example of the aliasing. Now, we're going to do another demonstration in a little bit that kind of expands on that. But the basic idea is that sampling has to happen fast enough to capture the reality of what you're doing. And there's some limitations on potentially what you're doing, particularly in signal processing environment, to make sure that you're sampling adequately, or that when you are sampling, you can prevent aliasing. And we'll talk about that in a little bit. So now we're going to talk about what happens in aliasing when we look at it in the frequency domain. And by frequency domain, I mean like our plot is showing here. On the vertical axis, we have energy or power, amplitude. And on the horizontal axis, though, we have frequency, starting at 0 down here and increasing as we move that way. Now we show 0, but actually when we have something like what we're demonstrating with a rotating system, or if we're sampling with complex values, we can also have negative frequency going the other way. And we just saw that in our demo that we did, that we just witnessed, where when we're matching the rotation rate with the sampling frequency, if we're a little bit lower than that, it looks like the blade's rotating backwards slowly. And so this region over here is actually useful because we have a rotating system. It has a forward rotation and a backward rotation. So there is such a thing as negative rotation. Rotating forwards we're going to call positive. Rotating backwards we're going to call negative. And we've seen it rotating backwards a little bit. We could spin it backwards if we wanted and sample it, and so that's useful spectrum down in that direction. As we mentioned before, our strobe is set up to sample at 12.5 times per second, 12.5 hertz. And any time that the blade is rotating in synchrony with that, it'll look like it's standing still. Well, what's that mean? If we're sampling at 12.5 hertz, that corresponds, we'll multiply that by 60, that corresponds to 750 RPM. And 2 times that, then, would be 1,500 RPM. So in this case, if the blade is turning at 750 RPM exactly, and we're sampling at exactly 12.5 hertz, it'll look like it's standing still because it's 1 full rotation per sample. This case then, 2 times f sub s would be when there's 2 full rotations per sample between samples, and it still looks like it's not rotating. Same thing with 3 times. Any integer multiple of the sample rate, it's going to look like it's standing still. So that winds up being, in our case, 750 RPM, 1,500 RPM, 2,250 RPM, and we just keep adding 750 RPM, and any one of those rotation rates will look like it's standing still for the blade. We have a little device here that we're going to use in the next demonstration, which lets us measure the rotation rate of the blade. It sends out a little infrared beam and looks at the reflections coming back, and that's why we put a reflector on one blade. And we have actually one on the underside of the blade too. But unfortunately, this thing's sensitive enough that it still sees both blades. Even though there's a reflector on only one, it gets a reflection from both blades. And so it reads twice the frequency that it's actually turning at. So in this case, if it's turning at 750, it would read 1,500. If it's turning at 1,500, it's going to read 3,000. And 2,250 is going to show 4,500, etc., etc. So we just have to keep that in mind. But what we're expecting to see, and what we're going to try and do in the demonstration, is look at these frequencies. Now, when it's running, when we're actually running the helicopter, it can't turn this slowly. It basically shuts off instead of being able to control the speed down that slowly. It basically, turn it on, when it comes on, it's turning at about 1,300, 1,400 RPM. That's kind of why we chose 12.5 samples per second, 12.5 hertz for the strobe rate, is we can catch this whole, what we call ambiguity region here, or region between where it looks like it's doing the same thing, where the alias is repeat, so to speak. So what we expect to see then is when the rotor is turning at 1500 RPM and we're sampling at 12.5 times per second, we expect there to be exactly 2 rotations per sample, and if it's at this RPM, it'll look like it's standing still. Same thing at 2250 RPM. In that case, there's exactly 3 rotations between every sample, and it's still going to look like it's standing still. Now it's maybe going to become a little bit more evident why we put a marker or reflector on just one blade and then put some black around there. Because if it rotates 1 full turn and a half, we'll be able to tell the difference between that and just 1 full turn, because otherwise the blades look the same and we can't distinguish where it's pointed that way or whether it's pointed that way. So what we expect to see then also is some cases where when we have not just an integer number of rotations, but an integer and a half, we expect then to see that there's a blur between the 2 blade tips, that it'll look like there's a reflector on each blade tip. And that'll give us a way to distinguish an integer number of rotations per sample between samples and an integer plus a half. Okay, so we can predict then that we will see a blurring of what the tips look like at exactly halfway in between these rotation rates. So halfway in between 1500 RPM and 2250 RPM is 1875. So what we're going to look for is that at 1875 RPM we see the reflector on both ends. Same thing then at 2625. We expect to see the reflective tip on both ends. We want to mention then too that let's notice what's happening here. We get this, like I say, they're called ambiguity regions, which is just multiples of the sample rate. And if we're exactly at f sub s, if we could turn the rotor at 750 RPM, it would look like it was stationary. And as we mentioned before, if it's a little bit less than that, it's going to look like it's rotating backwards. So say that we could rotate the rotor at, instead of 1500 RPM, at, let's say, for example, 1450 or 50 RPM less than this multiple or the sample frequency. What we would see is we can't tell that frequency. Again, we can't tell when it looks stationary whether it's really turning at some multiple of the sample rate or not. When it's 50 RPM less than the 1500 or any one of these multiples, we can't tell whether it's here or here. Basically, this is going to appear again at any multiple of the sample frequency. And what it's going to look like is that it's rotating at minus 50 RPM, right? Because when it's a little bit less than stationary, it's not quite made a full rotation between every sample. It's going to look like it's moving backwards. It's going to look like a negative rotation. So what it's going to look like is that it's really turning at minus 50 RPM. So these gaps are consistent then. When we have a gap, rotation rate of 50 RPM less than the sample rate, or if it was really turning at minus 50 RPM, that's what it would look like. So again, because it's a rotating system, it's a circular system, or if we had complex samples with a real and imaginary part of any kind of system, we can tell negative rotation from positive rotation, or negative frequency from positive frequency. So when we have this sort of complex or rotating system sampled, what we can get then is what we call our baseband, or our real region, I guess, or it is from f sub s over 2 to minus f sub s over 2 is what looks like reality. In other words, this 50 RPM less than 1500 looks like it's turning at minus 50. So if we really had it rotating at minus 50, that's what it would look like. So it's indistinguishable from really rotating at minus 50 RPM to 700 RPM to 1450 RPM. We can't tell the difference. That's why, again, why aliasing is a problem, is because you cannot distinguish what's going on in reality unless you do something to restrict your ambiguity region to only represent what you know you're sampling. The way you do this in a signal processing system is you filter out everything above half of the sampling rate. And then you know there's no energy out there that is possible to come in and alias. So that's why it's called an anti-alias filter, is you're trying to knock out everything from f sub s over 2 above, so that when you look at the signal, you know it was in here. That's basically it.
So we start out and we get this low RPM, and we're expecting at 1500 RPM that we can see a reflector on only one blade, the other blade's bare, and counter should read 3000. It's reading a little bit less than that, and that's why it looks like the blade's rotating slowly backwards. So if we speed it up a tiny bit, it should read a little higher than 3000 RPM, and sure enough it's 3107, 3106, 3113, and that's why it looks like it's spinning forward fairly quickly. So the next frequency that we're going to try is we're going to look for 1875 RPM, and it should have a reflector on each blade because there's 2.5 rotations per sample. And that should read 3750. It's reading, come on. It's rotating, looks like it's rotating a little bit backwards, and that's why it says 3730 instead of 3750. So if we try and speed it up a little bit, we're going to go up to, now we see a reflector on only one blade. So this is 3 rotations per sample, should give us a reading of 4500 RPM. 4450 we just saw, and that's why it looks like it's rotating backwards a little bit. 4456. The faster it spins, the noisier the reading gets. 4408, but a little bit less than 4450. That looks reasonable. Now we'll make it spin a little bit where it's rotating a little bit faster. 44 at 525, 4490. Now it looks like it's spinning backwards again. So it should read a little bit less than 4500, and we're seeing 4460. So now we should see a reflector on both tips because it'll be turning 3.5 times per sample, and there we go. Reflector on each tip, and we should see 5250 RPM, 5220 something. It's turning a little, it looks like it's turning backwards slowly. So 5170, 5160. Again, it's hard to get a reading that's stable because it gets a little noisy at these rates. 5140. It's about there, 5100 something. Okay, now let's see if we can get it to stable. Again, we should see about 5250. We see right at 5250. 5230.
So our demonstration went pretty much exactly as we predicted it to, in that for integer sample rates, for integer multiples of our sample rate, it looked like the blade was still and we had a reflector on only one tip and not the other. So it was an exact integer number of rotations per sample. 2 rotations for this case where it was turning at 1500 RPM, 3 for this case when it was turning at 2250. Remember, our indicator indicates double the rate. We also saw exactly as we predicted that halfway in between those, where we had an integer plus a half rotation, where it looked like we had a reflector on each blade because every other sample, the reflector would be on the other position. We saw those exactly where we expected and predicted to see them, which was at indicated 3750 and indicated 5250, which is double the actual rate that it was turning, really 2625 and 1875 RPM. So the nice thing about aliasing and sampling is they behave very predictably. It's always and forever going to be this repeating situation where you get this, the relationships of the ambiguity regions are very easy to analyze and predict what's going to happen. So if things go wrong, or if you have energy where you don't expect it to, it's not that hard to unwrap it and figure out what's going on. Nyquist, one of the guys that originally figured this out in the context of telegraph systems, came up with the usual criterion, Nyquist criterion, that we hear about, which is for a real valued system, whatever the highest frequency in a system is, you have to sample it at twice that. And that's basically what we figured out right here, was that if you want to support frequencies up to f sub s over 2, you have to sample it at least f sub s in order to make that non-ambiguous, so that you don't have energy folding back in as an alias. For a complex valued system, or for a rotating system like we've been dealing with, where you can tell negative frequencies from positive frequencies, you can support this entire bandwidth from minus f sub s over 2 to plus of f sub s over 2 unambiguously if you sample it at least f sub s. So in our case, we're sampling at 12.5 hertz. We will know without any possibility of aliasing that we get the right thing if we restrict the rotating system to run from minus 6.25 hertz to plus 6.25 hertz, or what's that turn out to be, 320 plus or minus 325 RPM. Whatever we see is really what's happening, and so we have to engineer the system to be that way. In a signal processing system, there can be noise coming in, there can be all kinds of spurious energy, you can have the electronics talking to each other, so you need an anti-alias filter that cuts off all energy above that frequency, so that you know it's not going to fold back in inside and fool you and trick you into thinking that there's something there that's actually someplace else. So this is why aliasing is important to understand. We hope our demonstration has made it clearer for you, or maybe answered some questions, or maybe taught you what aliasing is. It's not magic. It's very predictable. It's very workable. People know how to do this stuff. When things go wrong, you can, there's a way to figure out what happened and a strategy to fix it. So thanks for watching. I hope this was useful to you.